Today, we're diving into one of the most mind-bending technologies on the planet, quantum computing. Now, forget everything you know about just making computers faster. This isn't about a faster processor. It's like discovering a whole new species of machine. The jump we're talking about is like going from a single candle to a light bulb. It's that big a deal, and it's all powered by the strange, wonderful rules of the quantum world.
So here's how we're going to break it all down for you. First, we're going to play a game you are almost guaranteed to lose. Then, we'll get into the quantum rules that make it all possible. After that, we'll put quantum and classical computers head-to-head. Then, we'll zoom out and look at the global race for quantum supremacy. And finally, we'll explore how this incredible tech could solve some of humanity's biggest problems.
All right, ready to have your mind bent just a little bit? You know, to really get a feel for the kind of power we're talking about, we're not going to start with equations. We're going to start with a simple game of chance against a quantum computer.
So here's the challenge, plain and simple. It's you versus a quantum machine. The game? Just flipping a coin. Sounds pretty fair, right? Let's take a look at the rules. Okay, the rules are super simple. The coin starts out on heads. The computer gets a turn, then you get a turn. Then the computer gets one last turn. And here's the catch. You can either flip the coin or do nothing, and you don't know what the other player did. In the end, if it's heads, the computer wins. If it's tails, you win. With a normal coin, this is a total 50-50 shot. But when this exact game was played 372 times against a real IBM quantum computer, the machine won 97% of the time. Whoa! The handful of times it lost, those were just due to tiny errors in the hardware. So let's be clear, this wasn't a fair game. This was a quantum beatdown.
So how on earth is that even possible? I mean, it feels like cheating, right? But it's not magic, and it's not cheating. It's just physics, the incredibly weird and totally counterintuitive physics of the quantum realm.
To understand the computer's secret weapon, its ace in the hole, we need to meet the star of the show, the fundamental building block of all of this, the qubit.
Let's think about it like this. The computer or phone you're watching this on runs on bits, and bits are basically just light switches. They can be on, which is a 1, or they can be off, which is a 0. That's it. A qubit, on the other hand, is more like a dimmer switch. It can be a 0, it can be a 1, or it can be a whole fluid spectrum of possibilities somewhere in between.
This amazing both-at-once state is called superposition. The best way to picture it is to imagine a spinning coin. While it's in the air, spinning, is it heads or is it tails? Well, it's kind of both, right? It's just a blur of possibility until the moment it lands and you measure it. That's exactly how the quantum computer played the game. It kept the coin in that spinning, fluid state, so your move couldn't lock it into a definite outcome.
And if you thought that was weird, hold on, because qubits can also be entangled. Imagine you have two of these quantum coins, and they're magically linked. If you flip one and it lands on heads, you instantly know, that the other coin also landed on heads, even if it's on the other side of the galaxy. Their fates are completely intertwined.
This idea was so bizarre, so strange, that Albert Einstein himself couldn't quite wrap his head around it. He famously called it spooky action at a distance. And this spooky, instantaneous connection is one of the absolute keys to a quantum computer's unbelievable power.
Okay, so now that we have these new quantum rules in our back pocket, let's put it all together and really lay out the fundamental differences between a quantum computer and the classical computers we use every single day.
So it really all boils down to three things. First, the basic unit, a bit versus a qubit. We've got that. Second, the physics behind them. But the third one, power scaling, that's the real game changer. See, with a classical computer, if you want to double its power, you pretty much have to double the number of bits. It's linear. But quantum computers, they scale exponentially. Adding just one more qubit can literally double the machine's entire computational power. It's an explosion of processing capability. And you can bet that this kind of exponential power hasn't gone unnoticed. In fact, it's kicked off an incredibly high-stakes global race between nations to build the world's first truly powerful quantum machines.
And if you want a sense of the scale of this race, just look at this number. That's the estimated public investment from just one country, China, trying to get ahead in quantum technology. $15 billion.
This chart really paints a clear picture of the new global priorities. You can see China way out in front with that staggering $15 billion.
The European Union is also making a huge push, with a combined investment of around $10 billion. And then you see the US with a public investment of $1.8 billion. Now that number is a bit deceiving because it doesn't even include the massive R&D budgets from its private tech giants.
And what's really interesting is that different countries are playing to their strengths. The US might lead in private funding and the sheer quality of its research, but look at Canada. It has cleverly carved out a powerful niche in quantum software and cloud startups. Meanwhile, Japan is becoming the fastest-growing market in the world, which signals huge commercial potential. And India has launched a major national mission to build its entire quantum ecosystem from the ground up.
So, why this massive global race? Why all this investment? It's because quantum computing promises to help us solve problems that are completely, utterly impossible for even the world's most powerful supercomputers today.
Let's take drug discovery. Designing a new medicine means you have to predict exactly how a super complex molecule is going to behave. Classical computers can only guess at this, but a quantum computer, which, remember, operates on the very same quantum laws as the molecule itself, it could simulate it perfectly. This could let us design brand new medicines for diseases like Alzheimer's in a fraction of the time it takes now.
And the potential here is just staggering. I mean, imagine designing new materials literally atom by atom. We could build hyper-efficient batteries that transform our energy storage. We could create superconductors that work at room temperature, completely revolutionizing our power grid. We'd be engineering the future from the smallest possible level.
And the list just goes on and on. The applications touch almost every field you can think of. We're talking about creating unbreakable encryption to secure our entire digital world, developing financial models that can actually predict market chaos, forecasting weather with pinpoint accuracy, and of course, powering the next true generation of artificial intelligence.
You know, maybe the most profound application of all isn't just about solving problems, but about understanding our universe in a completely new way. As physicist Shohini Ghosh puts it, quantum computers are basically a window into a hidden reality that has always been there, just beyond our reach.
We are standing at the very dawn of the quantum age. It's a moment in history a lot like the birth of classical computing decades ago, and it leaves us with one huge inspiring question. Armed with this completely revolutionary new way of seeing and calculating reality, what impossible problems will we solve next?